Hi, sir.
Hi, Amy. How are you doing?
I'm good, thank you. How are you?
Good, very good. So, how's it going as far as calculus is concerned?
Yeah, all right.
Right.
The two topics that I just watched through your videos, they were
Hmm.
quite good. Yeah.
Okay, okay. Could you do some questions from your own textbook?
Yeah, there were just a few that I didn't get. I'll send them to you.
That'll be nice.
Yeah.
That'll be nice. Yeah. Okay. So today we'll move forward and take up the concept for. I'm thinking which next chapter should we pick up? Which are the areas which you think we should pick up now?
Um, well, I think once I do the overview thing for my book,
Yeah.
then you would see where obviously areas that I've missed or something. If
Okay.
some of them are like actual big topics, then could we focus on them? But if they're all just small things, then you can choose the next topic. I don't know. You said that
Okay.
one was like after integration or something, but that
Okay.
sounds so
Yeah,
complicated.
integration will be, we have to wait a bit more for integration. There
Okay.
are a couple of topics which are very important, which we need to cover in differentiation itself. So basically, I'm looking at two topics. One is under boundary conditions given to us, we have extreme values. So we could do that part for sure. So I think that could be a good idea to begin with. So, and second is that we have to do implicit differentiation, right? So the differentiation which we are doing basically is when we explicitly define a function in one particular variable, right? So then you always find dy dx and then figure it out, correct?
Yeah.
So these are the two major topics which are left. So let's begin with implicit differentiation today, okay? Let me share the screen with you and let's see. So can you see the screen?
Yeah.
Okay, so we'll talk about implicit differentiation today, and we'll cover these topics, which says first thing we need to understand what is implicit and what is explicit as far as functions are concerned. Then we have already done the chain rule. We'll apply the chain rule to find derivatives when the functions are given in the implicit form. When we say implicit and explicit, it really means that, earlier we were doing equations like y equals to mx plus b, right?
Yeah.
So here explicitly we are writing y in terms of x clearly, right?
Hmm.
Again, if we write that function notation, we say f of x is something like this, which is square root of x minus 1 plus 5 in this particular case. We're saying explicitly we are writing a function in terms of x. However, you have seen many times equation of circle and so many other functions which are kind of mixed up, right?
Yeah.
Here, just to give you one example, we could have an equation which could be x times y squared minus y cube equals to x squared. So in this particular equation, we still have the two variables x and y. We could
Hmm.
relate them some way or the other. However, they are mixed up. And it is kind of difficult to isolate y and explicitly write y in terms of x. You get the idea, right?
Yeah.
So that could be a situation. So basically, it means explicitly means clearly writing a function in terms of just one other variable, right? When we say implicit, that's not very clear. It's implicit, it
All
is
right.
implied. Okay, so they're actually mixed up. And sometimes you can isolate them also, but at times it may be very difficult to isolate. Now, here's another example. We have a rational function, and then on the other side, we have equals to y. Now, if you could cross multiply and kind of do some strategies, completing the square type of strategies to isolate y, you could do that, right? And then get y in terms of x. Perfect?
Yeah.
But that will sometimes be a huge exercise. So in calculus, we have means of differentiating a function directly when they are given in implicit form. So that is what we are going to learn today. Okay.
Yeah.
So let me share with you some examples to help with this concept of implicit and explicit functions. So what we said just now is that the explicit function is always defined as y equals to f of x, where y is isolated as a subject, right?
Mhm.
Now, in case of implicit function, it's kind of mixed up. So we are saying implicit function is defined as f of xy. So it's both mixed together, where y is not isolated as a subject. Okay? So broadly speaking, you can say something like this. Here are a few examples on implicit and explicit functions. You see this term 2xy equals to 3. So x and y is kind of together. They're not separated out, right? So
Yeah.
if I write an equation like this, it is implicit function. However, we could also take 2x on the other side and write y explicitly in terms of x, right? As y equals to 3 over 2x. You get the idea.
Yeah.
So the same function can be treated as both implicit and explicit. Here is another example of a circle with radius 4. The equation is x squared plus y squared equals to 16. You can actually isolate y, taking x squared to the other side, then square root. Now, when you do square root, you have to do plus and minus. You know, circle is not a function. It is a relation, right? If I draw a vertical line, it cuts at 2 points. So
Mhm.
what we can do is we can write it as two functions. One function, positive half, the other one, the negative half. Perfect?
Yeah.
So you could represent this explicit function, which is a relation actually, strictly speaking, x squared plus y squared equals to 16, as combination of two explicit functions, y equals to square root of 16 minus x squared, and y equals to minus square root of 16 minus x squared, correct?
Yeah.
So in the above examples, it was kind of simpler to, or I should say not very difficult, to isolate y and write it explicitly. Oh, here we have an example which is like x cubed plus xy plus y squared equals to x to the power of 5 y to y cubed. Something like that, right?
Mhm.
Now, it is very difficult to isolate y. Perfect. So what to do with such functions? Right? Still, we want
Yeah.
to analyze turning points and all those things. So fortunately, we have a means to do it, and that is what we will learn today, implicit differentiation. Is this part clear to you?
Yeah.
Correct. So let me share with you the two different approaches so that moving forward, you will understand how to do implicit differentiation. So let me take the very first example, which was 2xy equals to 3. You have already seen that it can be written in both the forms, right? So that means we could do the differentiation either way, right?
All
So,
right.
so we'll take this 2xy equals to 3. We can write this as y equals to 3 over 2x. Now, here are, let's say, draw this line here. Now, what you already learned is basically explicit differentiation. Okay, I changed the names here. So explicit differentiation is on the other side. Okay, that is cool. Right, so let's consider this explicit differentiation on this side, correct? So you could
Yeah.
isolate y equals to 3 over 2x, correct?
Mhm.
And then differentiate both the sides. You prefer to write x to the power of minus 1, and therefore I wrote like this. Does it make
Oh,
sense?
thanks. Yeah.
And then power rule. So minus and x to the power of minus 2, it comes in the denominator, and you get the derivative, that is dy dx equals to minus 3 over 2x squared. Perfect?
Yeah.
Easier to do. On the other hand, if I have implicit form xy equals to 3 over 2, I can still differentiate it using the product rule, correct?
Mhm.
So product rule means derivative of x times y plus derivative of y times x. That's what product rule is, right? So
Yeah.
derivative of x is 1, so we wrote y here, 1 times y plus x times derivative of y, dy dx as y prime equals to 0. Clear?
Mhm.
So we have this term xy prime, which can, from where we can isolate y prime, which is a derivative, dy dx. So once you do that, you get your result, which is minus y over x. correct?
Yeah.
Okay, now at this stage, you found dy dx, both the sides, they look different.
Yeah.
It is in terms of y, and this is in terms of x. I mean, here it is kind of mixed up, y and x, correct?
Oh,
So that's
okay.
a very typical part of implicit differentiation. Most of the time, when you do it, you get a result which will have both x and y,
All right.
right?
So both of them are equal, basically.
Both of them are equal, which I have shown here by substituting that y basically is equal to 3 over 2x, correct?
Oh,
And
yeah.
so I substitute this minus y with 3 over 2x. So when I do 3 over 2x times 1 over x times 1 over x, I get exactly what we got earlier.
All right.
Does make sense?
Yeah.
Okay. Now this was a very simple example. Since I could isolate y, I could do all this, right? Otherwise, I cannot do it.
Yeah, that's
Well,
true.
if I can isolate y, why will I go for implicit differentiation? I'll do explicit differentiation, correct?
Yeah.
Yeah. So the thing is that we will not always prove that both sides will be same. It is for us to understand that they will be
Mm.
same, right?
All right.
They will
Yeah.
be same. And it is very important to understand that this derivative will be having some relation in which the combination of both x and y will be there. Is it okay?
Yeah.
So that is the foundation for implicit and explicit. So, Amy, do you understand this?
Yeah.
Can you explain what you have understood?
So, what we've learned is implicit is where you can't isolate y, and explicit is where you can isolate y as like the subject. So, you've given three examples. First one being you can do it either implicitly or explicitly.
Correct.
So, you've shown how obviously you can just take y aside and make it the subject and get 3 over 2x and then find the derivative of that. But you can also do it you could also do it implicitly.
Yes.
Yeah. Which is what you've shown at the bottom there. Doing the derivative of the 2x and then the derivative of y, because that's the product rule.
Yes.
But what you've shown is you can do it both ways, but and you will get the same result. However, obviously, in some cases, like the third one shown, it can't be. You can't write it as an explicit function, so therefore you have to do it implicitly.
That is so true, right? So with this foundation, let's move forward. So if we have something like this, we'll prefer to do implicit. Even if we have combinations, most of the time, implicit could be better because isolating may take some extra steps, and implicit is also straightforward. You may have to apply the chain rule which you have learned earlier and get the result. Okay, so
All
let's
right.
take an example and see how it really works. So here we have a function which is we need to differentiate xy plus x minus 2y equals to 1, both implicitly and explicitly. So once again, we have an example where we are going to do both type of differentiation. So I've done explicit on the, um, I've interchanged this time. Oh, that is correct. Yeah, explicitly on the left side. So
Mm-hmm.
first thing is I have to isolate y, correct? Then only I can do explicit differentiation. So whatever
Yeah.
we were doing so far was all explicit differentiation, correct? So it was easy. We can factor y out from this equation. Once you do that, you get this y equals to 1 minus x over x minus 2, a rational function. Now
Mm.
we can apply the quotient rule. So I've directly applied the quotient rule and written the result. Derivative of numerator is minus 1 times the denominator minus derivative of denominator, which is plus 1 times the numerator, and square of the denominator, that is the quotient rule. Simplify this and you get 1 over x minus 2 whole square, right? So if you could
Mm-hmm.
isolate, very simple process, and there you go. Now let us say that we want to do without isolating to understand the process, correct? So we have again the same equation. We'll do differentiation with respect to x. Applying the product rule for xy, we get these two terms, correct? Derivative of x is 1 times y plus x times derivative of y, which is dy dx, right? Chain rule.
Yeah.
Now the other function x, the term gives you 1, and minus 2y gives minus 2 dy dx, the chain rule. Derivative of 1 is 0, correct? Now we have to isolate dy dx. That's what we are interested in. So we can take this as a common factor and then rewrite and get a result. As expected, you have a result where you have both x and y terms. Is that clear to you?
Yeah.
Correct? So that is how we are going to do it. So it's not very difficult. You can understand the process. Few steps you have to isolate dy dx and then do it. But at times when you can't help it, this is the only way to do it. Correct?
Just a quick question.
Yeah.
How do you know when, like, whether you differentiate with respect to x or y? Does it depend on the question, or?
Yeah, it depends on the question. Good question, right? So it could be either way. It could be either way. You could do differentiation with respect to x or y, but it was not specifically mentioned here. By default, we assume it is x.
Oh, okay.
So we just say gradient dy dx because by default, we put x along the horizontal x-axis and y is dependent on x. So when we are talking about two functions, y is the output represented on the y-axis, right? So, and that is a dependent variable. Independent variable is x. So we always differentiate with respect to the independent variable, correct?
Oh, right. Okay.
So we'll assume x to be the independent variable most of the time, if not mentioned. But that's a great question, right? Okay. Now, in these kinds of questions, we could have related, for example, I could now extend this question and ask you, how find critical numbers, or my question could be, where will the graph have a horizontal tangent line? So can you find a point on this graph where it will have a horizontal tangent line?
So would I just take the derivative and
Yes.
make it equal to 0?
Yes.
So that means y has to be -1.
Yes. So that is very clear. Now, when you were doing with this explicit differentiation, this is your derivative, and clearly this derivative is never 0, right? So
Yeah.
it's very clear from that particular answer.
Oh.
So you'll never have a horizontal tangent line. However, this situation is not very clear if I am working with this particular part of the equation. What am I going to do is, I'm going to equate, as you said, y equals to -1. And when I say y equals to -1, I'll sub y equals to -1 here, right?
Oh, yeah.
And I'll find the value of x. I'll
Yeah.
definitely get some value of x, which may not be relevant. You getting my point?
Oh,
Which
yeah.
may not be relevant. So it will give you the same result, but that may not be so obvious.
All right.
So the
Okay.
questions become very difficult when we ask a very simple question, with a function which cannot be explicitly defined. You get the idea,
Yeah.
right? So it's a very important note to think about, and I think you can now appreciate it. Let me take the next example, which is kind of the same thing. So, Amy, can you read this question for me, please?
Yeah. Find equation of the tangent line to the curve x² plus y² equals 25 at the point -3, 4.
Can you do this question?
What, like right now?
Okay.
Or you mean, have
How
I?
will you do this question implicitly? Tell me. Like,
Okay.
yeah.
Implicitly, right. So I would just find the derivative, so with respect to x.
Yes.
So like you've done ddx of x², add ddx of y², add ddx of 25.
Correct.
So ddx of x² would just be 2x. Ddx of y² would be 2y. Then the derivative of the inside function, so dy over dx.
Yes.
And then the ddx of 25 would just be 0 because it's a constant. and then we're trying to find dy over dx. So we keep that as the 2y dy over dx, and then move them minus 2x,
Yeah.
and yeah, and then we just cancel the 2's, and you get minus x over y.
Correct. We need to find at minus 3xy, substitute xy values, get your answer.
Yeah.
Wasn't that simple?
Yeah.
You see that? So
Yeah, it
it's
was
not
quite
very
good.
difficult. I mean, it's very simple. You could have done this by explicitly defining y. In that case, y will be equals to square root of 25
Yeah.
minus x squared, correct? And
That would
since
have been
we
so
are
long.
yeah, and since we are interested in a point which is minus 3, 4, we'll take y value as positive. So that particular half, which is the upper semicircle, right? And then you will have a radical function there to do differentiation, which will give you 1 over 2 square root
Oh,
thing. It's more complicated. Do you think about it?
yeah.
So first thing, we are isolating y. Second thing, we're complicating the question.
Yeah.
This is so straightforward. You get the idea.
Yeah.
So I've given a very good example just to make it friendly to you and so that you could try this out. So
Yeah.
don't be scared. Don't be scared because most students I've seen, they're very scared of implicit differentiation. I'm
It
not
sounds really big, but actually it's like quite straightforward, and it's handy because it's so much quicker than the explicit.
got the idea, right? It's
Yeah.
actually a very efficient way of doing it. And as you can now see, most of the functions are a combination of functions, and it may not be so easy to write them always implicitly or explicitly. Correct?
Yeah, that's true.
You cannot always write one as a subject and relate everything with that. It's very difficult. So it's a very practical approach, and we should actually get used to it. So if you have an opportunity to work with a function where you have an option to also redefine your function, don't go for that option. Just do it implicitly as we are doing.
Oh, okay.
That's my idea, right? Okay.
Yeah.
So, now onwards, when you do more examples, I'll give you a playlist to work with. Try to do them with implicit differentiation and see whether it makes sense or not, right?
Okay.
Many times in the examination, you'll get like questions like square root of x over y plus square root of something else equals to some number, right?
Yeah.
Now, this question, wherever you see square root of x and y, it is better to perform x implicit differentiation rather than, squaring
Oh.
and then solving. Also remember, when you're squaring both the sides, you are incorporating an error. Because when you square both sides, let's say we have minus 7, when you square, it's 49, and you don't know whether it was minus 7 or plus 7. You get my idea?
All right.
So
Yeah.
squaring means incorporating errors, and those kinds of questions in the examination hall, which you get, they are tricky questions. So if you do this transfer and then your result may be wrong.
It's not worth it. Yeah.
You have started with a wrong assumption, right? You get my
Yeah,
point?
that's
So
true.
there's a like heads up to you that if required, if you have something where mixed up things are given to you, just stick to implicit difference. Is that clear?
Yeah.
Now, the second half is straightforward. You need to write the equation of the tangent line. We prefer to use y minus y1 equals to m times x minus x1. Now, this equation is also preferred over y equals to mx plus p, since most of the time it is specified in the test paper to write the equation of the tangent line in standard form. So this equation gives you direct answer in standard form. It saves time. You get the idea,
Yeah.
correct? So that is very helpful, right? Here is a small note. Can you please read the note for me?
Implicit differentiation yields dy over dx in terms of both x and y. This is not constraint, but helpful in many situations.
Do you notice how? Very simple. Do you see that? Easy answer. We have a coordinate point. We just substitute that point, x and y taken care of. We got our answer.
Yeah.
You see that? So it's not a constraint. I mean, sometimes students feel that there are too many things to be done. Okay.
Mm.
It's not really a constraint. If you have answer in both x and y, it's good. I mean, not bad. I mean,
Yeah.
right? So let's take another example where it could be a constraint. So, okay, let's.
Oh.
Example number 3. Amy, can you read this question?
Yeah. So find the gradient of tangent to the point, to the graph of 2x squared over y minus y over x equals 1 at x equals 1.
Perfect. Now, this is kind of a difficult question. So on the graph, and I have actually shown the graph, this graph looks like this. Okay, so that's the graph. 2x squared over y minus y over x equals to 1 at x equals to 1. I'm not giving you y coordinate point. Do you see that part?
Yeah. Oh,
Oh,
yeah.
yeah.
No, I haven't my voice.
So sometimes in the test paper, especially when you're like right at the end thinking questions, this is what you're going to get, and this is there are extra marks, of course, for such questions. So first thing you should think about is I'm going to do implicit differentiation since we have x and y mixed up, right?
Yeah.
One thing, very clear. Second, I know that my result will be in terms of both x and y. I'm only given the value of x. I should find the value of y. Makes sense, right?
Yeah.
So before doing anything else, you should first find the value of y when x is equal to 1. Correct?
That makes sense. Yeah.
Substitute x equals to 1 in your equation, which is simple. You get 2 over y minus y over 1 equals to 1. You get a quadratic equation here, and that gives you 2 points for y. You get y as minus 2 or 1 for x equals to 1. You get 2 points.
Yeah.
As shown here on the graph, at x equals to 1, we have these 2 points A and B, where the y value could be minus 2, as shown at B, or 1. Got it?
Mhm.
Now, get back to the question. It says, find the gradient of tangent to the graph of this at x equals to 1. That means our answer will have two equations, one for point A, the other one for point B.
All right.
Correct. So now this is our thinking. When we have a question, good question, we have to think how to solve it within least amount of time. So we see that only x value is given to us. We have to find the y value. So first step, find y value. Second, we hit 2 points for y, means two equations. Remember that you have to give two equations, otherwise
All right.
marks lost, right? Now, we have our points A and B on which we have to find the equation of tangent line. But differentiation is easy for us. We have learned the techniques. We'll do both sides derivative with respect to x. And once we do that, independently you can work on these depending on which rule. Quotient rule will be applied in this case. Perfect?
Yeah.
Once you apply the quotient rule, and then you isolate dy dx, right? Now, in between these two steps is kind of very difficult. We know that we have to work at x equals to 1. Does it make sense? So
Yeah.
it's a good idea to simplify.
How do you simplify?
Just substitute x equals to 1. The equation the equation here is very complicated. It is 4xy minus 2x squared y prime over y squared minus xy prime minus y over x squared equals to 0.
Yeah.
So difficult to solve. Why are we doing implicit differentiation? Because the equation is too difficult for us to solve. You understand?
Yeah.
We cannot write explicitly what y is. Obviously, you have a very difficult solution here. Now, you have to make it easy. You know x is 1, correct? And
Yeah.
ultimately, we are interested in finding the derivative when x is 1. Of course, y will have different values. We'll see that later. But at least put x equals to 1, simplify your result. Do you see that part now? X is gone. X is 1. So I substituted x as 1 here, and I got what?
Oh, yeah.
I got 4y minus 2y prime over y squared minus y prime minus y equals to 0. Do you see that?
Yeah.
Much, much simpler, right?
Mm-hmm.
Now, one way, you could again isolate y prime and then work out, right? You could do that. Your choice.
Yeah.
But you know why? We know we have a very simple point A to work with, which is y is 1 for x equals to 1. Why not independently work and substitute y also as 1, simplify, and get your result? So in this particular equation
Oh,
right there, I substitute y equals to 1. So I'm doing part 1 now. At a, which is 1, 1, I'm trying to find the equation of tangent line first.
that makes sense. Yeah.
Now I'm going to isolate y prime. I know the derivative, that is the gradient. So the gradient at a, which is 1, 1, is 5 over 3.
Oh.
Is it?
Oh. Yeah, that works.
That works, right?
That's great. That was quite like smooth, that transition. I
Yeah,
thought you were gonna go like really complicated, but because we have one of the points, you might as well use it, you know?
use it. Second point is known to us, b equals to 1 minus 2. Substitute minus 2 for y now and get your result.
All right.
Simplify, get your answer. Does it make sense to you?
Yeah. Yeah. See, what I was thinking was, so we got our point, but because I'm always so focused on x, I'm thinking in the derivative, the simplified version that we found, there's no x anywhere. What do I do now? But I forgot that you had the y value.
Correct.
So, yeah. All right. That's not.
This is one of the most difficult questions which you'll get. And you see how simply we have actually solved it. One could just get lost at this stage what to do from here onwards, right? Because
Yeah.
it's too complicated to isolate y prime. Okay? So utilizing what is given to us, what we need to find, simplify as we move along and get your result. Result was find the gradient at the given point. There you go. That's our gradient. Done.
Oh wait, just quick things. Wait, so 4 minus 2y derivative minus y derivative. Is that not minus 3?
Pardon? Is there
Minus.
a calculation? Well,
No.
if there's a calculation mistake, then update. Okay, I might have done. Which place are you saying? Tell me.
So it says find the gradient of a, that one,
A,
and then
okay.
2 lines down.
Okay.
Minus 2y derivative minus y derivative.
Minus gradient minus 8. Okay, the second one you mean?
Yeah.
I said minus 2 for y. Oh, I see. When I say minus 2 for y, that will become...
Oh, no, that one's right. I was talking about the y equals 1, 1.
Okay, so y is 1, 1. So I'll substitute 4y, 4 minus 2y. This is 1. And denominator is 1. So minus y minus 1. That's okay. And when you open the bracket, this becomes plus 1. Yeah, there is a mistake, right? So this will be plus 5, right?
Yeah.
Plus 5, correct? So no, that's right.
No. Wait, so it is, no, plus 5. But then what about did you just switch it around? Because it will be minus 3y derivative.
Yeah, there is a mistake.
Plus 5.
Yeah. So minus 2y prime, and that is minus, so that is minus 3y, right?
Oh, right, yeah.
Correct? One thing. Second, 4 plus 1 is plus 5, correct? Yeah, I actually took it to the other side. Let's do like this. Is that clear?
Okay, yeah.
Let's do like this, okay? Plus 5. Now, if you want to take it to the other side, now both are opposite sides. So you can take 3y dash on the other side. So you get 5 over 3. You get the same result.
All right, okay.
Correct? But anyway, try it out. I could do some calculation mistakes. That is fine. But have you understood the method?
Yeah, it's really clear.
Really clear, yeah. Yeah, I think I skipped one step here because I wanted to keep that positive. Y prime, I wanted to keep that positive. So I did.
Oh, okay.
I
was just wondering. Yeah.
Missed one step, right? That's true. Okay, anyway, Amy, can you explain me the solution of this particular example?
Yeah. So because they've given us that it is at x equals to 1, we haven't got the y value. So the first step is to find the y value. So all you do is sub x equals to 1 into the function.
Correct.
And we get a quadratic. So we get y squared plus y minus 2 equals 0. We can expand it and get y equals minus 2 or y equals 1. So we've got 2 points. That means we need to have 2 equations at the end, like 2 gradients.
Okay.
So just keep that in mind, because if you just write 1, then you lose half marks.
Okay.
So then now you've got the 2 points, A being 1, 1, B being 1 minus 2. You simply find the derivative of the function. So d dx of 2x squared over y minus d dx over y over x equals d dx over d dx of 1, which would just be 0. And you'd use the quotient rule.
Yes.
And then you get that really like complicated quadratic. So we need to make it more simpler because that's really hard to deal with. So we've been given that it will be at x equals to 1. So we just sub that value in, and we get 4y minus 2y prime over y squared minus y prime minus y equals 0.
Perfect.
So once you go up to there, then we just found the 2 points. And because we're going to have the 2 gradients, all you do is sub in the y value, which we got as 1 here, into the equation. And you get 4 minus 2y prime minus y prime minus 1 equals 0. Then we simplify that, keeping the like prime thing positive. So we get 3y prime plus 5 equals 0. So we get y prime equals 5 over 3. And that's the gradient of the tangent at the point 1, 1.
Correct.
And now we have to find the gradient at point B. So we just do the same thing again and sub in the y value minus 2 into the equation and go through all those steps, and we get y prime as minus 16 over 10. So that's the other gradient.
That's how you do it, right? Absolutely clear?
Yeah. How many marks would that be worth, roughly?
Around 6 marks.
Wow.
Yeah. Now let's take the next example, which is, can you read this question for me?
Find the stationary point or points on the graph of x squared plus y squared minus 4xy plus 3 equals 0.
What is stationary point?
So that's where f of x equals 0.
Derivative.
The derivative, I meant that. Yeah, sorry.
Gradient. Yes, the gradient is 0, right? That's what it is, right? Now, I have given that S means you might expect more than 1 point. Is that clear?
All right.
Make a note of this. So whenever in a question it is that, you should look for more than 1 point, right? It is possible. Because normally they won't put that S there, right? Secondly, whenever we have this type of thing where we have y squared, we know it is not a function, it's kind of a relation. And in a relation, and when especially dealing with circles, there may be 2 points with the same gradient, right?
Mm-hmm.
Because the symmetry of the circle itself. So when you read the question, you have to get this thing straight in your mind that, again, we're looking for 2 solutions, right?
Oh, okay.
Now, at stationary point, the gradient of the tangent line will always be 0. We have an equation, we'll differentiate with respect to x. We're going to apply the product rule. Once we apply the product rule, you get your equation in terms of y prime, isolate y prime, and you simplify to get your expression. Is that clear?
Yeah.
2y minus x over y minus 2x. Now the question is, find the stationary points. How will you do it now? You already have the gradient expression.
Mm-hmm. Oh, make the gradient expression equal to 0.
Perfect. So make it to 0 for stationary points. And now that really means that the numerator is 0, right?
0. Yeah.
2y minus x is 0. That means x is equals to 2y. Perfect.
Mm-hmm.
You could have written y equals to x over 2, but why?
I was just about to ask that.
Don't write fractions, okay?
Oh, okay.
Now, when we are working with x and y, just think about a and b and right both at par, right? Don't think about dependent, independent. Go easy stuff, right? Don't complicate your questions, because I've seen that substitution of y equals to x over 2, and then students get lost, right? What happens? Imagine all these
Things that
fractions.
you make.
Oh my God, it's like hell.
Things
So
that you make you easier for yourself. Yeah, but you're not.
one wrong step, you're like disaster, right?
Mm-hmm.
Okay, now you substitute x equals to 2y in the given equation, right? Simple quadratic equation to solve. And as expected, you get two values for y. Once you get these two values of y, substitute back into your equation to find x. So there's more work, right? It's not that simple. Okay? So
Or could you sub it into that
back
one?
to the equation, substitute back into this equation, find the value of x for each, +1 and for -1 separately.
Oh.
Is that clear to you?
But if I know this is wrong, but if you subbed in like plus or minus one into, you know, where you wrote down x equals 2y,
Yeah.
you would still get plus or minus
Oh,
2,
yeah,
but that
yeah.
would be
I'm
wrong,
sorry.
right?
Don't go there. You're so right. Don't go there. Yeah, substitute back here.
Wait, can you do that though?
Yes, 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 yes.
Into the, oh,
That's
okay.
what I did. Sorry. Yeah. X equals to 2y, so twice, right? So instead of plus minus 1, for plus minus 1 y values, you get plus minus 2 for x values, correct?
Mm-hmm.
Yes. I mean, you're absolutely right. And there you go. Write clearly your answer. The stationary points are this and this. Perfect.
Yeah.
So what do you learn from this particular example?
I learned about implicit differentiation and how it's our friend. It's really good. So when you can't isolate y, and obviously it would look really complicated, but when in doubt, even if you can do it like explicitly, I think just stick with implicit differentiation because you're never going to go wrong, and you got like one less thing to kind of like worry about. So yeah, you'd find the derivative. Usually it's with respect to x because you said it's independent of y.
Yes.
Yeah, and all of that y-axis and x-axis thing. So that's handy, and you have to be like read the question carefully before you even attempt the question. There are so many little points and hints that you would get. So if it says stationary points, the first thing you write down is f prime x would have to equal 0. So you just have that point in your head. If it said point or points, you should understand why it said points. So obviously there could be more than one. So just bear that in mind. And yeah, use sub values in to equations, and when it gets really like complicated, if they've given you a value like x equals 1 or something, always try and use what the like question's given you, because that's obviously there to help you. So sub it back in and make it more simpler for you to manage. And even like in this case, when you had x equals 2y, don't try and do y equals x over 2, because like let's try and avoid all these fractions and radicals and all these like complicated things. Yeah.
That is
So,
correct. Yeah.
mm,
So I think with this, we end up our session on explicit and implicit differentiation. So we understand what exactly it is, when to
yeah.
do what, right? When to do what. Now, can you summarize our learnings for today?
Yeah, so what we learned is so if it says explicit differentiation, that means we can isolate y as a subject, and implicit differentiation is where you can't isolate y. So that's when you have to find the derivative with respect to x. So you kind of do that for each part of the equation. And you find so dx of each of the different constants and
That
things.
is so correct. Yeah.
Yeah, and when you so if they give you points or things, don't immediately start the question if they've only given you one part of the variable, like let's say x equals 1. Obviously you should wonder where's the y value, and if they've given you the function, just sub it in, get the y value, so you've got a coordinate point to work with. And yeah, always try and simplify it, make it easy for yourself. Don't go into fractions and things and make it really complicated, because like Sir said, if you're going to start squaring things and things, that's where the errors will start coming in, because it gets really complicated and you don't want room for error. So yeah.
That's so right. So I think you've summarized it beautifully. You've understood the concept. I'll actually share with you a playlist on this particular topic. Try the questions out and let me know if there are any difficulties, right?
Yeah.
And in our next lecture, we'll take up the next topic, which is what? We'll work on the extreme values, absolute maximum and absolute minimum, right? So that'll
Okay.
be our next topic. Get ready for that. Okay?
Okay, cool. Thank you so much, sir. I
Thanks.
really appreciate it. Thank you.
Thanks. Bye.